Hello and welcome to today's webinar. I'm Joe Nebbia with Newport Partners, and I'm going to be talking this afternoon about indoor air quality sensors and a project we're working on through the Department of Energy's Building America program to develop test methods for low-cost indoor air quality sensors, with the goal that these sensors could eventually be used to dynamically control our ventilation systems. So I'm glad that you've joined me today. If you have questions throughout, this is going to be a fairly brief overview of the project and what we're doing. Please enter your questions as you think of them in writing via the question portal, and I will spend the last few minutes of the webinar answering questions. I expect this webinar to go from 1 to 1:30 and then spend somewhere between 10 and 15 minutes answering questions, depending on how many you have. So with that, I'd like to get started, and thank you again for joining me. So our current state of the ventilation industry, it shouldn't be a surprise to most of you on the webinar today, but it's pretty basic as far as how we approach design of our ventilation systems. We typically have a ventilation rate that's maybe developed using ASHRAE 62.2 standard or the International Residential Code or International Mechanical Code, depending on what you're building. And we're looking at number of bedrooms and floor area and determining how much CFM we need of ventilation that way. And that's a basic summary. It can certainly get more complicated than that, but we're usually coming up with one rate for a fan running all the time, or perhaps we're coming up with a rate for a fan that runs only part of that time. We're talking about whole house mechanical ventilation. And then spot ventilation, there are other code requirements related to how much air that fan has to move. But typically we don't see a lot of demand response ventilation or ventilation that responds in other ways than an on-off switch or possibly some sort of timer schedule. So it's a pretty basic approach to ventilation, and it works fairly well. But one of the things we're trying to discover is if we can find a way to improve both the efficiency of the ventilation system in not over ventilating a space when the fan or system doesn't need to be running, and then also not under ventilating a space and we have pollutants present and the baseline CFM of our fan is not moving or dealing with the issue correctly. So our goal is to find a way to dynamically control our ventilation based on the actual presence of pollutants. Again, when pollutants aren't there, the fan can turn off and we can save energy, and when they are present, we can make sure we're getting that the ventilation system continues to run until the pollutants are gone or at a safe level. So if we're cooking on a range or cooktop of some sort and we're creating a whole lot of PM2.5 and other indoor pollutants in the kitchen, we want our range hood, for example, to know that it's got to turn on when it senses the presence of PM2.5 and exhaust that pollutant. And then we want it to turn off again when the pollutants aren't there. So in order to be able to do that, we have to know about the concentration of pollutants or the relative concentration, depending on your control. And we have to be able to integrate that with the ventilation system. The problem is that, or excuse me, I'll get to the problem in a moment. So more of the concept here is that, let's say we're cooking or we're in a shower where we have some aerosolized particulate matter, something like that, and we've got PM2.5 in the house, or perhaps we have humidity in those bathrooms coming in, and maybe we've got formaldehyde throughout the house, off-gassing from different products in the house. Our VOCs from our paints and our carpets and other things are present there in the house, and then we've got something like CO2, which is, isn't a pollutant per se, but which does have an effect on cognitive function, and you don't want the levels too high. It's a whole bunch of nasty stuff that can be in our houses. But what if when we turned our fan on, or we had a system that turned the fan on when it saw these pollutants, and in the kitchen and the bathroom exhaust, we get rid of our PM2.5 when it's there, and we get rid of the humidity in the bathroom based on an RH sensor. And then formaldehyde sensor maybe would run the whole house ventilation system and dilute that pollutant. For VOCs, same thing. If they're present, we would want to know and be ventilating the space. And then finally, CO2, something like that. Maybe we're just telling the ventilation system that there's an occupant present and we want to be ventilating for that reason. And then we want that system to turn off once it's no longer needed and we don't have that pollutant presence. The problem that we're running into is that research grade sensors, something like a federal reference method or federal equivalent method monitor for a PM2.5 or something like that, or just a really robust, well-made sensor that maybe doesn't meet one of those EPA designations, but still is meant for outdoor air quality sensing and for really high-end research type projects. Those tend to cost a lot of money, and we're talking, somewhere from $8,000 to hundreds of thousands of dollars, depending on the sensor and the pollutant it senses and the sophistication. Even at the low end of that range, that's not something we're going to be able to integrate successfully with a residential ventilation system or even a consumer feedback device. So that's the barrier to this idea currently. We know those sensors work pretty well, but we can't put them in a home. There are quite a number of low-cost sensors on the market. Lots of different manufacturers have made them, different customer feedback units. Sometimes it's just the raw sensor that will go into different products, but there are a number that are low cost, and they might range anywhere from $50 to $700 is what I've seen on the market. And they vary in what they do. Some have multiple pollutants that they cover. Others simply focus on one. But those low-cost sensors, the problem is we really don't know how well they work because there is no standardized way of testing them. Most manufacturers do significant testing on their own products as they develop, but there isn't a standardized way where we can look at different sensors and know how they're going to perform relative to the rest of the market. Or we also don't know how well a sensor is going to perform relative to a control that we might have. So an example of that might be if I've got a sensor that is not particularly good at predicting an accurate pollutant count. So maybe it's off by, a factor of 100 or something like that. But it does tend to show change in pollutants fairly well. So in other words, we do see a percent change, even though the actual concentration count isn't accurate. A ventilation manufacturer might want to know, okay, this sensor will work for me as long as I can set my controls to respond to changes in pollutants rather than absolute concentration levels. So that's a sort of question we want to know about these sensors, how they work and how well they work. But again, there's no set way to test them. So that's why we've come up with this process and why the Building America program is funding us to work on this project to develop a test method for that eventually we hope will become a standard for testing these low-cost sensors. Our process that we've gone through in the project so far is to form a pretty robust advisory group with experts in the sensor field, lab experts, ventilation industry representatives, government agencies, and also members of the ASTM subcommittee that will eventually need to get this through if it's to become a test method. So after we formed that group, we also took a state-of-the-art existing procedure based on a prototype test chamber and developed that procedure into consensus language that could actually be used in a standard, got agreement and feedback from the advisory group on what needs to be in that test in order to make it rigorous and yet still cost effective for manufacturers to put their product through. We now have a consensus draft of that test method through that process. And I say consensus, not yet an ASTM consensus, but just within our working group. And we have drafts for both PM2.5 and CO2 sensors. And then currently where we are is on this fourth step, which is performing laboratory testing to demonstrate that the method is actually doable and that test conditions that are described in the test method are achievable. Once we do that, we'll make any necessary adjustments based on what we found in the testing and introduce it at ASTM. The D2205 subcommittee at ASTM, which deals with indoor air quality, has already approved the work item, which is allowing us to start developing some consensus on this. And then once we finish our testing, we intend to introduce it to them to go through the ASTM consensus process. But the Building America program through Department of Energy is funding us for this technical development piece early on. So the goal is once we have a test method, we will be able to then push it out to industry, which I'll talk about a little bit more later. This is just a summary of our project team. Newport Partners is my firm. We're managing the project and also bringing in standards development expertise. From the ventilation industry, we have the Home Ventilating Institute and their research arm, HARCA, who are in charge of industry outreach and bringing in that ventilation perspective. And then our lab partner on this project is the South Coast Air Quality Management District's AQ-SPEC lab. They were the ones who developed this prototype test chamber and initially started testing sensors so that we could have a straw man to begin with developing our test method from. And they also bring a lot of sensor testing expertise. And then, of course, our funding is from the Department of Energy's Building America program, and they're providing also project oversight for this study. After we finish, the goal is that if we have a standardized test method, low-cost indoor air quality sensors can be reliably tested and shown to have a performance that the ventilation industry is comfortable with, the Home Ventilating Institute can then use their certified products listing program to list and label smart ventilation systems that use tested sensors as part of their controls. So the process here is we figure out how to test them, we test them, then the ventilation industry can put some sort of backing behind those products, and we hope that will help with builder and homeowner adoption in the end. Our advisory work group is pretty broad, and we were very happy to have good representation from the sensor industry. You'll see EPA and NIST, as well as the Department of Energy has been involved. Over on the right, several other groups that are on that ASTM subcommittee, good representation from the ventilation industry, and 3 different labs have been giving us feedback on this test method as we develop it. And it went through, I don't know, 10 to 12 drafts of the different the test methods before we had something we felt like we could start testing, and we're still improving the language and all that stuff to make sure it fits within ASTM's requirements and also is clear and repeatable for another lab that might do this. So the two pollutants we decided on, we had funding enough to develop test methods for two pollutants, or PM2.5 and carbon dioxide. And the reason we settled on these two, we wanted a aerosol, which is why we picked PM2.5, and PM2.5 is one of the major pollutants we're concerned about in kitchens and other places indoors because of the aerosolization of particles at a certain size that have long-term chronic and also acute health effects on humans. Excuse me. So we wanted one that dealt with aerosols and then another that would deal with some sort of gas. And we picked CO2 not because it's necessarily a pollutant that has a dramatic health effect, but because there are a number of CO2 sensors on the market that are low cost with quite a lot of variation in the quality of those sensors. So some of the other gases that were present, we felt like had at least more sophistication in their sensors. Other ones didn't have many sensors on the market. And then there were some practical limits, like formaldehyde we would have loved to deal with, but the reference sensor that we would need to compare against was cost prohibitive. So we settled on these two, and the goal is that these test methods can later be used as models for test methods for other gases, sensors for other gases, because you could look at the CO2 method and much of the process would be the same, although interference and concentrations and some of the equipment would change as you change gases. But we hope that the process will be repeatable for other gases and that those test methods can follow through the ASTM process after this project. So we have quite a robust test for both gases. We are doing 5 test phases, anywhere between 600 and almost 1,100 data measurements, depending on the test method and the type of sensor. We do have a minimum test time, and I'll explain that a little bit more later. And then we have an accelerated aging process that we've included in order to make sure we're knowing how these sensors will perform at least after some amount of time in the field. So that's a summary. If you look at the PM2.5 testing phases, and again, I'll just put in a reminder here, please put in any questions you have in writing and I'll get to them at the end. We're doing phase 1 in PM2.5 testing. We do 6 different concentrations and we're taking 20 measurements at each concentration. The test is designed not with a specific amount of time for testing. We have a minimum testing time, but it varies significantly based on the sensor you're testing and then also the makeup of your chamber. If your volume is different, it will take longer to get to steady state. And I might be testing a PM2.5 sensor that has a time resolution of 1 minute, which means I'm taking data every minute. In that case, it's going to take me 20 minutes at steady state to get 20 measurements. But if my sensor has a time resolution of 5 minutes, I'm going to be testing at that concentration for an hour. So that's why there's no set time for this test. There will be a range of times that are needed. In the next phase, we're testing different temperature and relative humidity combinations to see how climatological effects will impact the sensors. If it gets hot or cold, or we add a lot of moisture, or it's really dry, how does that impact the accuracy and the response of these sensors? And again, taking 20 measurements at every temperature and relative humidity combination. For interference, we're testing 3 different interference, which in this case for PM2.5 are all different size particles. Those tend to be the interference which are going to impact a PM2.5 sensor at 4 different concentrations. And then we'll take measurements, 20 measurements at each interferent concentration in order to see the impact of those interference on our reading of PM2.5. Next, we have a temperature cycling phase, and this is that accelerated aging process that we go through. It was impractical to do a standard accelerated aging where you might, in sensors, for most sensors, what you'd want to do is expose it to a extremely high concentration of a pollutant for an extended period of time, and then test again to see how the sensor holds up. The problem with that is that method essentially destroys the chamber equipment and the reference monitors that we're comparing against, which is not sustainable as a test method. So we came up with this idea, one of the sensor manufacturers recommended it, to do temperature cycling, because this will imitate mechanical stress. So you take, the concept is you take the general temperature you would see throughout a day, temperature change, and then you broaden that range in order to concentrate the amount of time you would need to mimic the change. And we go through 163 cycles at the 10 to 50 degrees Celsius range. Essentially mimics a year's worth of mechanical stress on these sensors. And then we repeat the concentration experiment for phase 5 to be able to measure drift between that first phase and the 5th phase after what's a simulated year's worth of mechanical stress. So we don't have years and years of accelerated aging, but we do have a year's worth of stress involved in the test. CO2, I'm not going to go through this in as much detail just because it's all of the same phases. The only difference really is that there are 5 concentrations we test, and that the interferent we're concerned with, instead of different particle sizes, we're concerned with humidity. So we're testing RH at different levels and seeing how it impacts that the CO2 measurement of the sensor. Again, taking 20 measurements for each of these phases for the sensor. So that's the basic approach to the test. Now I'll show a schematic of how it could work. This is just an example. Any lab could really develop their own as long as it fits within the general requirements of the test method. The concept here, if you look over on the left of the screen, you're bringing in ambient air and it's passing through a zero air system, which is essentially scrubbing impurities out of the air. You could scrub a whole lot of things out of it. The minimum required for the test is that you're removing particles from the air, and so you'll have a filter of some sort so that we have particle-free air entering the chamber. And then we introduce PM2.5 into the chamber in a controlled way. And in this test method, you would need some sort of fan to move the pollutant around in the chamber. We don't specify CFM or anything like that because that's going to depend on your chamber volume. But they essentially have to be able to mimic the test conditions as written in the test method, which establishes a steady state metric for that chamber. And the way we tell steady state is we actually have those really expensive reference monitors that we talked about at the beginning. Each chamber would need something like that in order to compare the test sensor, the low-cost sensor again. So we've got the federal research method or federal equipment method monitor, which we know works well. It's been tested through an EPA process, and we're going to compare the test sensor, the low-cost sensor, to that monitor. So we know that the chamber is at steady state when the reference monitor tells us that, and then we can start taking those 20 measurements per the test method. So that's how the general idea of the chamber test works. Similarly with CO2, we're bringing in ambient test air. There's no real practical way that we could come up with to scrub CO2 out of the air, which is why we started a baseline level of 450 ppm concentration of CO2 rather than specific concentration tied to, say, the limit of detection of the reference monitor, which is extremely low in CO2. Scrubbing that amount of CO2 out of ambient air is just extremely costly. So we have a higher baseline that we're testing to. It's not really zero air. And then we're adding CO2 to reach different calibrated levels, and that's going to probably need to go through a dilution calibrator to get the right amount of CO2 into the chamber. And likewise, we're comparing the test sensor, the low-cost sensor, to a more research-grade sensor for CO2. There's no federal reference method for that type of sensor, so instead we're referencing best available technology for the reference monitor. But other than that difference, it's essentially the same process that we're going through for CO2. Right now, we're in the process of doing lab testing for those two pollutants. We have 4 different sensor models we're testing, 3 of each model, so we're testing them in triplicate, and it will take 3 to 4 weeks per sensor, most likely, to get through the test with our prototype chamber, South Coast Air Quality Management District's prototype chamber. What we discover during this test will require us to adjust the draft test method language. One example we're running into now is just difficulties in generating the interferent concentrations for the different particle sizes in the PM2.5 test as written in the test method. So we're having to come up with additional guidance on how to achieve those concentrations, and that's an adjustment we'll have to make. It will then be sent back to the working group to approve any adjustments before we move on to ASTM to wrap up the process. This is just a picture of the prototype test chamber. You can see it from a few different angles. If you're a lab person, this might be more exciting than for others, but it's a pretty sophisticated piece of equipment, lots of different sensors and scrubbers and things like that. And it is a one-of-a-kind at this point. We're hoping that other labs will build their own if this does become a consensus standard. And finally, you can see here that was just a brief video of the nebulizer process where salt solutions are being turned into particulate matter and introduced into the chamber. I believe that was the coarse particle generator there for the interferent particle sizes for the PM2.5 sensor. So that's what we've been working on. Again, the goal of this is that eventually we'll be able to test sensors for many different pollutants depending on what they sense, and that it will be a standardized process that we can use for any low-cost sensor. Really, any sensor could try it, and then that the ventilation industry would be able to adopt sensor-controlled ventilation strategy so that we can better address the issue of indoor pollutants in the home. So with that, I'd just like to open it up for questions. If no one has questions, we don't have to spend a lot of time on this, but But if you do have questions, please submit them now. Anyone is welcome to contact me and ask me more questions. But this is a good time to get it in. Here's a question here, asking a question about tight home 80 CFM fans in the bathroom with a timer every 10 minutes. So I think the question there is that significant? I would recommend we start at least by, I'm not seeing it necessarily a question there, but I would recommend we start at least by what's required by ASHRAE 62.2 as far as ventilation rates. That would be the industry best practice. Depending on the size of the home and number of bedrooms, that approach might work. And then there's all sorts of discussions you could get into about exhaust only versus supply only and balanced ventilation and what the best strategy is there. In our situation here, those bath fans we hope would turn on based on pollutant presence, and maybe it's a sensor somewhere else in the house that tells us, okay, people are here, we need to be running the ventilation system. Maybe they're ventilating based on a relative humidity sensor, which would probably make a lot of sense, or a PM2.5 sensor. So any other questions? I hope I answered whatever the question was there, but if not, please let me know. Feel free to email me afterward if I don't get to your question. Any other questions? Okay, well, thank you for, oh, there doesn't look like there's any questions. Thank you for joining me. Like I said, if you do have questions or want to talk more about what we're doing in the Building America program, we're happy to talk about it. We're also involved currently in a project that's developing a smart range hood based on this kind of a concept. So we're doing a lot of work in this space, and we're really excited about it. So I hope you have a great rest of your day, and please, you should be able to get to this webinar if you want to listen again through the registration link, or we'll be posting it on our website as well as a recording.